All right, hi again. Yoni Nazarathi here, again with the Mathematical Engineering of Deep Learning by Benoit Lequet, Sharat Mocha, and myself. I'll do another proofread section readout, and this is of section 1.5. That is Deep Learning as a Mathematical Engineering Discipline. So while compute power and the abundance of data are key to the success of deep learning, the importance of mathematics cannot be underplayed. We now explain the term mathematical engineering and justify its use in the book's title. Human engineering of systems has relied on mathematics almost since the dawn of time. The pyramids of Egypt could not have been constructed without some prior geometric calculations. And later down the road, the machines that drove the Industrial Revolution were designed with the aid of trigonometry, algebra, calculus, and other mathematical techniques. For such reasons and others, the term engineering mathematics is often used to describe the combination of calculus, linear algebra, basic differential equations, Fourier analyses, Laplace transforms, and many other mathematical tools that can interplay to help design and develop physical engineered systems. So why does this book use the permuted term, mathematical engineering? Our answer lies in the fact that in the field of deep learning, mathematics is used directly as an engineered component. When one designs an electrical circuit, the flow of electricity is engineered, and hence the field is called electrical engineering. When one designs a robot arm, the mechanics are directly considered, and hence the term is used mechanical engineering. What about the design of a deep neural network for deep learning? The specification of deep learning models is a mathematical specification about the flow of data through a combination of affine functions, nonlinear functions, and at times other mathematical components. Hence, the design of deep learning models is the act of mathematical engineering. To further understand the phrase mathematical engineering, consider the following display borrowed from chapter 5. It represents an action that is at the heart of deep learning. So in this display, we see A superscript L minus 1 going through an affine transformation that becomes Z superscript L. The affine transformation is a matrix W superscript L times A plus B superscript L. And then there's an activation where A superscript L is the output of the activation. The activation is called S. That's applied to Z. And all of this is F sub theta with superscripts L. The point is that the function F sub theta superscript L represents a mathematical action of a single layer of a deep neural network on neurons or activations or inputs, A superscript L minus 1, to obtain neurons, activations, or outputs A superscript L. It involves an affine transformation to reach an intermediate value, Z superscript L, via matrix multiplication by the weight matrix W superscript L, and an addition of a bias vector, that's B superscript L. It then involves the application of a nonlinear activation function, S superscript L. The trainable parameters of the layer are W and B, both with superscript L, and their combination is denoted via theta, also with superscript L. A deep neural network, F sub theta, is then a functional composition of many such layers, say capital L of them, where Y is the output of F sub theta of X, and that is the functional composition of many such functions, and there's an equation for that, where X, the input, is A superscript 0, and Y, the output, is A superscript capital L. The parameters of the whole model, theta, are comprised of the individual parameters of the layers, theta superscript 1 through theta superscript L. Some aspects of the mathematical engineering of deep learning involve choosing the nonlinear functions, S superscript L, and other aspects involve defining the dimensions of W superscript L and B superscript L, as well as any sparsity structures in these. Importantly, deep learning training is essentially the iterative solution of an optimization problem where the decision variables are the many components of theta. For such a problem, in addition to specifying efficient optimization algorithms, one needs to determine the optimization objective, which in the language of deep learning is called the loss function. All these activities and many more comprise the mathematical engineering of deep learning. The mathematics used. While deep learning is quote unquote deep, the application of mathematics in the field is relatively shallow. The mathematical engineering of deep learning is mostly based on linear algebra, multivariate calculus, and basic probability. It thus uses mathematics at a level comparable to the first 2 years of university studies of an engineering degree or a similar field. In fact, even within these fields, one mostly requires only elementary operations, and there's not much reliance on theoretical results. For example, in terms of linear algebra, matrix multiplication operations are key, but vector spaces, eigenvalues, and matrix decompositions are mostly not essential. Similarly, in terms of calculus, derivatives and their multivariable counterparts are central to the field, but integration, vector fields, manifolds, or properties of real functions are mostly not used. Finally, in terms of probability, one simply needs to account for basic probabilities and occasionally evaluate expectations or variances for random variables. This accessibility of deep learning has motivated pedagogical approaches focusing on a practical coding perspective, such as in deep learning for coders with FastAI and PyTorch, as well as, and there's a reference 5, as well as many other resources. See also the notes at the end of this chapter. In contrast to such code-centric approaches, our approach relies on mathematical notations as a means of communicating ideas. With our approach, even though theoretical mathematical results are mostly not essential, mathematical notation plays a central role in conveying ideas concisely. See also section 1.6, where we introduce basic notation for the remainder of the book, as well as a few supporting mathematical results summarized in the appendices. Development and investigation of deep learning via advanced mathematics. It's important to note that while the mathematics used in this book is quite simple, many of the models and techniques that we present have advanced underpinnings, advanced theoretical underpinnings. These advanced counterparts have often played a role in the development of the current simple models. One such case, which will become evident in chapter 3, is a logistic regression model. With this model, one can analyze the model as either a simple neural network or alternatively position it as a statistical model leveraging on the slightly more advanced theory of maximum likelihood estimation, MLE. Interestingly, historically, logistic regression was first developed using MLE and only later appeared as a basic machine learning model. Similar trends in the machine learning community are also in association with support vector machines, SVM, a topic that we did not cover further in the book. The theory and application of SVMs hinges on beautiful mathematical results from functional analysis, and their popularity has certainly inspired multiple ideas in deep learning. Nevertheless, deep learning models can be understood without considering SVMs. Other such examples where more advanced mathematics are lurking behind the scenes is in our consideration of the optimization algorithms in chapter 4. In this context, while most of today's methods are simple first-order optimization methods, the path to realize that, at the moment, these techniques work best has also gone through the study of much more advanced second-order optimization techniques and their variations. We also mentioned that there is ongoing research on the theoretical properties of deep neural networks. In this domain, researchers make use of functional analysis, measure theory, information theory, stochastic processes, differential geometry, topology, category theory, and other mathematical fields to describe and understand theoretical properties of deep learning. While such research efforts are very exciting, they are not the topic of this book. So thank you. That was the end of section 1.5, which covered deep learning as a mathematical engineering discipline. Thank you.